Welcome back to Whispering Universes, where we explore the quiet mysteries hidden in the vast darkness between the stars, and tonight we turn our attention to one of the cosmos's most haunting and beautiful phenomena. Worlds that wander alone through the galaxy, forever exiled from the warmth of a parent star, drifting through the emptiness with no sunrise to mark their days and no seasons to measure their years. Imagine, if you will, a planet much like Earth or Jupiter, with mountains or storms, perhaps with moons orbiting close enough to raise tides on hypothetical oceans, but surrounded not by the familiar light of a nearby sun, but by the distant cold pinpricks of starlight scattered across the galactic plane. This world experiences no day, no night in the way we understand those concepts, only an eternal twilight illuminated by the faint glow of the Milky Way itself. The temperature at its surface, if it has a solid surface, hovers just a few dozen degrees above absolute zero, cold enough to freeze any atmosphere into snow and ice, cold enough to still molecular motion almost completely. Yet this world is real, not imagined, and it is far from alone in the universe. These are the rogue planets, the wanderers without a sun, and recent discoveries suggest they might be among the most common objects in our galaxy, perhaps outnumbering the stars themselves. For every point of light you see in the night sky, there might be dozens or even hundreds of these dark worlds drifting unseen through the spaces between, following their own lonely orbits around the galactic center, remnants of violent planetary system formations, or perhaps worlds that formed in isolation, never knowing the embrace of a parent star at all. Here on Whispering Universes, we have explored many strange corners of the cosmos together, but rogue planets represent something particularly profound in our understanding of how planetary systems form and evolve. They force us to reconsider what we mean by the word planet itself, to acknowledge that the neat arrangement of worlds orbiting stars that we see in our own solar system might be the exception rather than the rule, and to confront the reality that the universe contains entire populations of objects we are only beginning to detect and understand. The study of rogue planets is barely 2 decades old as a serious observational science, yet already it has transformed our view of galactic structure and planetary formation. These worlds challenge our detection methods, requiring techniques that can find objects that emit almost no light of their own and reflect no light from a nearby star. They exist at the very edge of what our telescopes can perceive, and yet their numbers and their implications for understanding how solar systems evolve make them essential targets for current and future astronomical surveys. Tonight, we will journey together through the science of these lonely wanderers. We will explore how astronomers discovered them against all odds, how they came to be ejected from their birth systems or formed in isolation, what conditions might exist on their dark surfaces, and what they can teach us about the architecture of planetary systems across the galaxy. We will consider the physics of their exile, the dynamics of their wandering, and the remarkable possibility that some of these worlds might harbour life in subsurface oceans, heated by internal sources, living ecosystems that have never seen a sun. As you settle in for sleep, let your mind drift outward with us into the spaces between the stars, to these silent worlds that spin in darkness, to understand what they reveal about the cosmos and our place within it. The universe, we are learning, is far stranger and more populated than we ever imagined, filled with worlds we cannot see but can detect through their subtle gravitational influence, through the faint infrared glow of their cooling bodies, through the mathematical patterns that emerge when we study planetary system formation in detail. Let us begin our exploration of the rogue planets, the wanderers of the cosmic dark, the worlds that challenge everything we thought we knew about how planets exist and what forms they can take in the endless night between the stars. Throughout the history of astronomy, our definition of what constitutes a planet has evolved as our observations have expanded and our understanding has deepened. For most of human history, Planets were simply the wandering stars, those points of light that moved against the fixed background of the celestial sphere, distinguished from stars by their motion, but assumed to be fundamentally similar in nature. Then came the Copernican revolution and the understanding that planets are worlds like Earth, orbiting the Sun in a cosmic dance governed by gravity and inertia, each following its own elliptical path through space. This heliocentric model became so fundamental to our thinking that the very word planet became inextricably linked with the concept of orbital motion around a star. When we discovered planets around other stars in the 1990s, beginning with the hot Jupiter orbiting 51 Pegasi, we simply extended our solar system-based definition to these new worlds, considering them planets because they orbited their parent stars just as Earth orbits the Sun. The architecture seemed universal. Stars in the center, planets in orbit around them, a hierarchy of mass and gravity that organized systems into stable configurations. But the universe, as it so often does, proved to be more creative and more diverse than our limited experience had suggested. The first hints that planets might exist without stars came not from direct observations, but from theoretical work on planetary system formation and dynamics. Computer simulations of young planetary systems in the 1990s and early 2000s showed that gravitational interactions between planets could lead to dramatic instabilities, with planets scattered into highly elliptical orbits or ejected from their systems entirely, flung into interstellar space by gravitational slingshot, encounters with more massive worlds. These theoretical predictions suggested that the spaces between the stars might be populated with worlds that had been born in orbit around a star, but had lost that connection through violent dynamical interactions. Such worlds would be planets by any reasonable definition, with masses in the planetary range, with compositions similar to the planets we knew, with the same basic structure and formation history, but lacking the one thing we had always assumed was essential: a parent star providing light and heat and gravitational order. The realization that such rogue planets might exist opened up an entirely new domain of astronomical investigation. If planets could be ejected from their birth systems, then every planetary system that formed, including our own, likely lost some of its original members to interstellar space. The population of rogue planets wandering the galaxy might preserve a record of planetary system formation and evolution, a fossil record of the violence and chaos that characterized the early epochs of system development before stability was achieved. But recognizing that rogue planets might exist and actually detecting them proved to be very different challenges. A planet that orbits a star can be found through its gravitational influence on that star, through the slight wobble it induces in the star's position, or the dimming it causes when it passes in front of the star as seen from Earth. A rogue planet, having no star to interact with, cannot be found by these methods. It emits no visible light of its own, reflects no starlight, and exists in the vast darkness between the stars, where even the accumulated glow of the galaxy is barely sufficient to illuminate it. The question of how to detect these dark wanderers seemed almost insurmountable at first, requiring either extraordinary luck or entirely new detection techniques that could find objects based on properties other than their light emission. Astronomers realized they would need to exploit the one thing rogue planets definitely possess: mass, and therefore gravity. Any object with mass curves the fabric of space-time around it, and light passing near that object will follow the curved paths created by this gravitational field, bending in ways that can be detected and measured if the geometry is favorable. This gravitational lensing effect, predicted by Einstein's general theory of relativity and confirmed through observations of starlight bending around the Sun during solar eclipses, offered a way to detect massive objects that emit no light of their own. If a rogue planet passed in front of a distant star, as seen from Earth, its gravity would focus the star's light, causing a temporary brightening that would betray the presence of the unseen world. The technique required monitoring millions of stars continuously, waiting for the rare alignment that would allow detection, but it offered a path forward for finding planets that could not be found any other way. And so the search began, driven by theoretical predictions and enabled by new wide-field telescopes capable of monitoring vast numbers of stars simultaneously, looking for the subtle signature of gravity made manifest in the temporary brightening of distant points of light, seeking to populate our maps of the galaxy with worlds we could not see but could detect through their gravitational influence on light itself. The first serious attempts to detect rogue planets through gravitational microlensing began in earnest in the early 2000s, building on techniques and infrastructure that had been developed for other purposes, particularly the search for dark matter through its gravitational effects on light from distant stars. Several large-scale surveys pointed their telescopes toward the densely populated star fields near the galactic center, where the probability of alignment between a nearby lensing object and a distant background star reaches its maximum, and began the patient work of monitoring millions of stars night after night, waiting for the telltale brightening that would indicate a massive object passing between observer and star. The Ogle survey, the optical gravitational lensing experiment, operated by the University of Warsaw and using a telescope in Chile, became one of the primary sources of microlensing detections in the first decade of the 2000s. The survey monitored roughly 200 million stars in the galactic bulge, taking images every clear night and using sophisticated software to identify variations in brightness that might indicate a lensing event. Most of the events detected were caused by ordinary stars, their gravity focusing the light of more distant stars as they passed in front of them along our line of sight. But a small fraction of events showed characteristics that suggested something different, something smaller and darker than a star. In 2011, a team of astronomers analysing Ogle data and data from other microlensing surveys announced a remarkable finding. They had identified a population of microlensing events with durations much shorter than those caused by stellar lenses, typically lasting only a few days or even hours rather than the weeks or months typical of star-caused lensing. The short duration indicated that the lensing objects had relatively low masses in the range of planets rather than stars, and the fact that these events showed no evidence of a nearby stellar companion suggested that the lensing objects were isolated, wandering through the galaxy without a parent star. The analysis suggested that these objects, which the team called free-floating planets or rogue planets, might be extremely common, with their population possibly exceeding the number of stars in the galaxy by a factor of nearly 2. Implications were staggering. If the analysis was correct, then for every star visible in the night sky, there might be 2 or more planetary mass objects drifting unseen through the darkness, a hidden population that might contain more total mass than all the stars in the galactic disk combined. The announcement generated considerable excitement in the astronomical community, but also some skepticism about the interpretation of the data. Microlensing events are inherently ambiguous, with the light curve, the pattern of brightening and dimming over time, containing limited information about the lensing object. The same light curve could in principle be produced by different combinations of mass and velocity, and distinguishing between a nearby low-mass object and a more distant higher-mass object requires additional information that is often not available. Some researchers questioned whether all of the short-duration events attributed to rogue planets might instead be caused by other phenomena, or by planets that actually did have parent stars, but at distances too large to produce detectable signals. Follow-up observations and more sophisticated analyses in subsequent years have refined these early population estimates, generally confirming that free-floating planetary mass objects exist in significant numbers, but suggesting that the population might be somewhat smaller than the initial 2011 estimates indicated. The exact number remains uncertain, with different studies producing estimates ranging from roughly 0.25 rogue planets per star to perhaps 2 or more per star, depending on assumptions about mass ranges and detection efficiency. What is clear from the accumulated microlensing data is that rogue planets are not rare curiosities, but a significant component of the galactic population. Whether they outnumber stars or merely approximate stellar abundance, they represent a major category of objects that we are only beginning to understand and characterize. Each microlensing detection adds another data point to our growing statistical picture of these worlds, helping us understand their mass distribution, their spatial distribution across the galaxy, and the mechanisms that might have produced them. The Ogle survey and other microlensing efforts continue today, with improved cameras and analysis techniques allowing detection of ever smaller objects. More recent microlensing surveys have begun to push down into the mass range of terrestrial planets, detecting candidate rogue worlds with masses similar to Earth or even smaller. These detections suggest that the population of rogues includes not just gas giants, comparable to Jupiter or Saturn, but also smaller rocky worlds, perhaps entire planetary systems worth of ejected terrestrial planets drifting through the dark. As the census of rogue planets has grown, each detection has brought with it new questions about where these worlds came from, how they acquired their lonely trajectories through the galaxy, and what conditions might exist on their dark surfaces. The first glimpses of darkness revealed through microlensing have opened a new chapter in planetary science, one that requires us to think about planets not as appendages of stars, but as independent objects in their own right, worlds defined by their mass and composition rather than by their orbital relationships. The challenge of detecting rogue planets lies in their fundamental invisibility across most of the electromagnetic spectrum. A planet that orbits a star can be found through the light it reflects from that star, or through the slight dimming it causes when it passes in front of the star as seen from Earth, or through the subtle wobble it induces in the star's motion through space. A rogue planet, divorced from any stellar source of illumination and emitting negligible light of its own, can be detected only through more subtle means, through the bending of light caused by its gravitational field, or through the faint infrared glow of heat slowly escaping from its interior. Gravitational microlensing, the technique that has produced most rogue planet detections to date, exploits the fact that any mass curves space-time around it, creating gravitational fields that deflect light passing nearby. When a rogue planet passes almost directly between Earth and a distant background star, the planet's gravity acts as a lens, bending the star's light and focusing it toward our telescopes. For a brief period, typically lasting hours to days depending on the planet's mass and velocity, the background star appears brighter than usual, its light magnified by the gravitational lens. Then the alignment shifts as the planet continues its motion through space, and the star returns to its normal brightness. The lensing event complete. The beauty of microlensing as a detection technique lies in its mass sensitivity and its ability to find objects at great distances. Because the amount of gravitational lensing depends only on the mass of the lensing object and the geometry of the alignment, microlensing can detect objects with masses as small as Earth's, or even smaller in favorable circumstances. The technique works equally well for planets orbiting stars and for rogue planets wandering alone, though distinguishing between the two requires careful analysis of the light curve and, ideally, detection of anomalies that reveal the presence or absence of a stellar companion. The typical microlensing detection of a rogue planet proceeds through several stages. First, automated software monitoring millions of stars identifies a brightening event consistent with gravitational lensing, a smooth symmetric increase in brightness followed by a symmetric decrease. The duration of this event and the degree of magnification provide initial constraints on the mass and distance of the lensing object. For stellar lenses, the event typically lasts weeks to months and reaches magnification factors of 2 or more. For planetary mass lenses, the duration is much shorter, often just days or hours, and the magnification is typically more modest, perhaps 1.5 times normal brightness or less. Once a candidate rogue planet lensing event is identified, astronomers attempt to gather as much information as possible before the event ends and the alignment geometry changes. Multiple telescopes at different locations on Earth may observe the event, providing different perspectives that help constrain the lens's properties. The precise shape of the light curve, how quickly it rises and falls, the degree of symmetry, and any small deviations from the expected smooth pattern all contain information about the lensing object's mass, velocity, and distance. The challenge comes in the interpretation of this data, because microlensing light curves are inherently degenerate, meaning that different combinations of mass, distance, and velocity can produce very similar observed patterns. A nearby low-mass object moving quickly can produce the same light curve as a more distant, higher-mass object moving slowly. To break this degeneracy, astronomers use statistical arguments based on the expected distribution of objects in the galaxy, on typical velocities for different populations of objects, and on the known geometry of the galactic disk and bulge. For rogue planets, an additional diagnostic comes from searching for evidence of a stellar companion in the light curve. If the planet actually orbits a star, but at a relatively wide separation, the star's gravity will produce its own subtle effects on the light curve, tiny deviations from the smooth rise and fall expected for an isolated planet. The absence of such stellar signatures provides strong evidence that the detected object truly is rogue, wandering alone through the galaxy without a parent star. More recently, astronomers have begun to supplement microlensing with direct imaging techniques in the infrared. Young rogue planets, those ejected from their birth systems within the last few 100 million years, still retain significant heat from their formation, glowing faintly in the infrared, even though they emit no visible light. Wide-field infrared surveys using telescopes like the Wide Field Infrared Survey Explorer WISE have identified candidate rogue planets based on their infrared colors and lack of association with any nearby star. These direct detections complement the microlensing results, providing different information about the rogue planet population, particularly about young, recently ejected worlds. The most promising avenue for future rogue planet detection may be the Nancy Grace Roman Space Telescope, previously known as WF-IRST, planned for launch in the mid-2020s. This space-based observatory will conduct an extensive microlensing survey with sensitivity sufficient to detect rogue planets down to Mars mass, or even smaller, potentially revealing a population of small rocky worlds that current ground-based surveys cannot reach. The Roman telescope's location in space, above Earth's atmosphere, will provide superior image quality and continuous monitoring capability that ground-based telescopes cannot match, enabling detection of extremely brief microlensing events that would be missed from the ground. Through these various techniques, gravitational microlensing for statistical population studies, infrared direct imaging for young rogues, and future space-based surveys for complete characterization, astronomers are gradually illuminating the dark population of rogue planets, finding ways to study worlds that by their nature resist observation, using gravity and residual heat as the signatures that betray their presence in the cosmic dark. The population of rogue planets spans an enormous range of masses and compositions, from massive objects at the boundary between planets and brown dwarfs, with masses perhaps 10 or 15 times that of Jupiter, down to small rocky worlds comparable to Earth or even Mars, and possibly smaller still, extending into the realm of objects we might call rogue asteroids or rogue moons, though at those small masses the distinction between a planet and a captured smaller body becomes increasingly arbitrary and perhaps meaningless. The gas giant rogues, the Jupiter and Saturn analogues, that have been ejected from their birth systems, represent one distinct population with relatively well-understood properties. These worlds form through gravitational collapse in the outer regions of protoplanetary disks, accumulating massive atmospheres of hydrogen and helium around rocky or icy cores, growing until they reached masses sufficient to prevent further accretion or until the disk's gas dissipated. When such a world is ejected from its system through gravitational scattering, it carries its entire atmosphere with it into interstellar space, though the coldest outer layers may eventually freeze and precipitate as molecular snow. Without a nearby star to provide external heating, a rogue gas giant's temperature is determined entirely by internal heat sources, residual heat from formation that slowly escapes over billions of years, heat from gravitational contraction as the planet settles into its final configuration, and heat from radioactive decay of heavy elements in the core. For a Jupiter-mass rogue planet that was ejected a few billion years ago, we can calculate that the effective temperature, the temperature its surface would need to radiate away the internal heat flow, equals roughly 50 to 100 Kelvin, far below the freezing point of any substance except perhaps helium under extreme pressure. At such temperatures, the upper atmosphere of a rogue gas giant would be extraordinarily cold and dark, with any methane, ammonia, or water vapor condensing into ice clouds that precipitate downward through the hydrogen-helium envelope. The planet would appear almost completely black in visible light, reflecting only the faint starlight of the galaxy and emitting no light of its own in visible wavelengths. In the infrared, however, the planet would glow faintly, its thermal emission in the 3 to 10 micron wavelength range revealing the presence of residual internal heat, a signature that allows detection of young rogue giants through direct imaging. The structure of these worlds deep below their visible cloud layers would remain similar to that of giant planets in normal solar systems. The hydrogen atmosphere would transition to liquid metallic hydrogen at depths where pressure exceeds a few million Earth atmospheres, and below that would lie the core, probably a mixture of rock and ice, with perhaps 10 or 20 Earth masses of material compressed to densities several times that of lead. If the planet had moons when it was ejected, some of them might have remained bound, continuing to orbit the now dark world, raising tides in its atmosphere and perhaps generating additional heating through tidal friction. The population of smaller rogue worlds, terrestrial planets, comparable to Earth or Venus, presents very different conditions and challenges. A rocky planet ejected into interstellar space would cool much more rapidly than a gas giant, its smaller mass providing less gravitational binding energy, and its lack of a massive atmosphere reducing insulation. Within perhaps 100 million years of ejection, such a world surface would freeze completely, any oceans transforming into global ice sheets that might eventually reach depths of kilometers as atmospheric gases condensed onto the surface as snow and ice. However, even such a frozen world might retain liquid water beneath its icy shell if conditions are favorable. The ice itself would provide insulation, and radioactive decay of uranium, thorium, and potassium in the planet's interior would continue to generate heat for billions of years. Computer models suggest that a rogue Earth with a thick hydrogen atmosphere, perhaps captured during formation or retained from an early phase of atmospheric evolution, could maintain subsurface liquid water through greenhouse warming of the ice layer and geothermal heating from below, creating conditions broadly similar to those beneath the ice shells of Jupiter's moon Europa or Saturn's moon Enceladus. The exact boundary between frozen death and potential habitability for rogue terrestrial planets depends sensitively on several factors. The planet's mass, which determines both its gravitational binding and its initial heat content, its composition, particularly the abundance of radioactive elements that provide long-term heating, its atmospheric composition and pressure, which determine insulation efficiency and the presence of any large moons that might provide tidal heating. A more massive terrestrial planet with a thick atmosphere and one or more large moons might remain hospitable to liquid water and potentially to life for billions of years, despite its exile from stellar warmth. At the small end of the rogue planet mass range, we encounter worlds that blur the boundary between planets and moons, objects with masses comparable to Earth's moon or the Galilean satellites of Jupiter. Too small to have retained significant atmospheres, but large enough to have undergone internal differentiation and to retain some geothermal heat. Such objects, if ejected from planetary systems, would freeze solid almost immediately, their surfaces reaching equilibrium temperatures of perhaps 30 or 40 Kelvin, cold enough to liquefy oxygen and nitrogen, cold enough that molecular motion nearly ceases. The diversity of rogue planet types, from massive gaseous worlds to tiny frozen rocks, reflects the diversity of the planetary systems from which they were ejected. Each rogue planet carries with it information about its formation environment and ejection mechanism, information encoded in its mass, composition, and thermal state. As our detection techniques improve and we begin to characterize individual rogue planets rather than just measuring their aggregate population statistics, we will learn to read this information using rogue planets as probes of planetary system formation and evolution throughout the galaxy. As microlensing surveys have accumulated, detections and infrared surveys have identified young rogue candidates, astronomers have begun to build a statistical picture of the rogue planet population, estimating how many such worlds exist in the galaxy and how they are distributed across different mass ranges and regions of space. This census work proceeds through a combination of direct counting of detected objects and sophisticated modeling that accounts for detection biases and incomplete sampling of the population. The most fundamental question about rogue planets concerns their total abundance relative to stars. The early 2011 microlensing results suggested a population of roughly 2 Jupiter-mass rogue planets for every star in the galaxy, implying something like 400 billion rogue gas giants wandering through the Milky Way. More recent analyses have revised this estimate somewhat downward, with current best estimates suggesting perhaps 0.25 to 1 rogue planets per star in the Jupiter mass range, though with substantial uncertainties arising from the difficulties of interpreting microlensing data and accounting for all possible sources of bias in detection efficiency. If we accept a middle ground estimate of roughly 1 rogue planet per star, this implies a galactic population of approximately 200 billion rogue worlds with masses comparable to Jupiter or larger. To put this in perspective, if we could somehow transport all of these rogue planets back to stellar systems and distribute them evenly, each star in the galaxy would gain 1 additional gas giant, dramatically altering the architecture of most planetary systems and potentially triggering new episodes of dynamical instability and further ejections. The mass distribution of rogue planets, how their numbers change as we consider progressively smaller masses, remains one of the key uncertainties in the current census. Microlensing surveys are most sensitive to Jupiter mass objects, with detection probability dropping rapidly for smaller masses due to their shorter duration lensing events and smaller magnification. Extrapolating from the detected population to estimate the abundance for Earth mass or smaller rogues requires assumptions about how the mass function. The relationship between mass and abundance continues toward lower masses. Different theoretical models of planetary system formation and evolution make different predictions about this mass function. If most rogue planets are ejected through gravitational scattering, we might expect the population to be dominated by massive gas giants, because these are the planets most likely to interact strongly and to eject smaller worlds while remaining bound themselves. But if ejection can occur through other mechanisms, perhaps through close encounters with passing stars during the early phases of cluster dissolution. Smaller terrestrial planets might be ejected just as efficiently as gas giants, leading to a population weighted toward lower masses. Some models suggest that the total number of rogue planets might be dominated by small worlds, with perhaps 10 or more Earth mass rogues for every Jupiter mass rogue, implying a galactic population measured in the trillions. Other models suggest a flatter mass distribution, with roughly similar numbers of rogues in each logarithmic mass bin. The truth likely lies somewhere between these extremes, but determining the actual mass function observationally requires surveys capable of detecting Earth mass and smaller rogues, surveys that are only now becoming technically feasible. The spatial distribution of rogue planets also contains important information about their origins and history. Microlensing surveys detect rogues primarily in the direction of the galactic bulge, where the high density of background stars maximizes the probability of lensing alignments. But this selection effect makes it difficult to determine whether rogues are concentrated in the bulge region or distributed more uniformly throughout the galactic disk. Theoretical expectations suggest that rogues should follow roughly the same spatial distribution as stars, since they formed in association with stellar systems, but with some differences arising from their velocity distribution and from the fact that younger rogues, more recently ejected, might cluster near star-forming regions. Future surveys will map the distribution of rogues across different regions of the galaxy, from the central bulge to the outer disk to the galactic halo, providing tests of formation models and revealing whether different rogue populations exist in different environments. We might find that metal-rich regions near the galactic center produce more rogues per star because their planetary systems form more massive gas giants that drive stronger dynamical instabilities. Or we might find that metal-poor regions produce their own population of rogues through different formation mechanisms, perhaps through more frequent stellar encounters in dense clusters. The census also extends to characterizing properties beyond just mass and abundance. For the handful of rogue planets detected through direct infrared imaging, astronomers can measure colors and spectra that reveal information about atmospheric composition and temperature. These measurements have shown that young rogue planets, those ejected within the last few 100 million years, can have temperatures of 500 to 1000 Kelvin or more, hot enough to maintain warm atmospheres and complex atmospheric chemistry despite their isolation from stellar heating. As this census continues and detection techniques improve, we are gradually populating our maps of the galaxy with the invisible presence of rogue worlds, adding a new component to our understanding of galactic structure and creating new questions about how common planetary ejection truly is and whether our own solar system has contributed its share of rogues to the wandering population. While most rogue planets remain purely statistical objects, their presence inferred from brief microlensing events that provide little information beyond mass estimates and rough distances, a small number of individual rogue worlds have been studied in sufficient detail to begin characterizing their properties and perhaps understanding their histories. These particularly well-observed rogues serve as prototypes for the larger population, giving us glimpses of what conditions might prevail on worlds that wander between the stars. One of the best characterized rogue planets bears the designation PSO J31T522, a name derived from the Pan-STARRS survey that discovered it in 2013. This world was identified through direct imaging in the infrared, its thermal emissions standing out against the background sky despite the lack of any nearby star. Follow-up observations with multiple telescopes and in multiple infrared wavelengths revealed that PSO J31T.522 has a mass roughly 6 times that of Jupiter, placing it near the upper end of the planetary mass range, though its exact mass remains somewhat uncertain due to the difficulty of measuring masses for isolated objects. What makes PSO J31T522 particularly interesting is its youth and its apparent isolation. The object lies about 80 light-years from Earth, in the constellation Capricornus, moving through space with no stellar companion visible within several light-years. Spectroscopic observations show that its atmosphere contains methane, water vapor, and probably complex carbon compounds, with a temperature around 800 Kelvin, hot enough to glow visibly in the near-infrared. This high temperature indicates that PSO J31T.522 is young, probably no more than 12 million years old, still radiating away the heat of its formation. The color of PSO J31T.522 in infrared images appears distinctly pink or magenta, a consequence of its atmospheric composition and temperature. The methane in its atmosphere absorbs certain infrared wavelengths more strongly than others, creating the distinctive color signature that helps distinguish it from stars and brown dwarfs of similar temperature. This pink rogue planet, Gusea, has become iconic in the study of free-floating worlds, one of the first rogues whose individual properties could be characterized rather than merely statistically inferred. Another well-studied rogue planet candidate, WISE J147241324213, discovered by the WISE Infrared Space Telescope, lies much closer to Earth, perhaps only 10 to 15 light-years distant, making it one of the nearest known free-floating planetary mass objects. This world appears cooler than PSO J31T.522, with a temperature around 250 Kelvin, cold enough that it barely glows in the infrared at all. Its mass is estimated at roughly 5 to 10 Jupiter masses, though again with substantial uncertainty arising from the difficulty of mass determination for isolated objects. WISE J14724.10204.21.3 might represent an older generation of rogue planets, worlds ejected from their birth systems long enough ago that they have cooled significantly and now exist in a state more typical of what we expect for most rogues, dark and cold and nearly invisible except to sensitive infrared instruments. If this object truly is a rogue planet, rather than an extremely low-mass brown dwarf, its proximity to Earth makes it an invaluable target for future detailed study, perhaps including attempts to detect and characterize any remaining atmosphere through high-resolution spectroscopy. The challenge in studying these individual rogues lies in distinguishing them from other populations of objects that might appear similar. Brown dwarfs, failed stars with masses between about 13 and 75 Jupiter masses, occupy a mass range that overlaps with the most massive rogue planets. Young brown dwarfs can have temperatures and colors very similar to young massive rogue planets, and without a clear way to measure mass precisely, astronomers must rely on indirect indicators to determine whether a given object formed through planetary processes in a disk or through direct gravitational collapse like a star. Age provides one useful diagnostic, because young, low-mass objects could potentially be either planets or brown dwarfs, but very low-mass objects that appear old must be planets, since brown dwarfs of the same mass would still be hot enough to glow more brightly. Spectroscopic features related to surface gravity also help distinguish planets from brown dwarfs, because planets have higher surface gravities for a given temperature due to their smaller radii. The presence of certain molecules, like methane at relatively high temperatures, can indicate low surface gravity, and therefore a likely planetary nature. For PSO J31T.522 and similar young directly imaged rogues, astronomers have used kinematic arguments to support their planetary classification. These objects move through space with velocities and directions consistent with membership in nearby young stellar associations, groups of stars that form together and are still loosely bound by their mutual gravity. If PSO J31T.522 formed as part of one of these associations, it must have been ejected from a planetary system within the association, supporting its classification as a rogue planet rather than a brown dwarf. The handful of well-characterized individual rogue planets provides crucial calibration for our understanding of the larger population. Each detailed study adds constraints to our models of what rogue planets look like, how they cool over time, what atmospheric properties they retain, and how we might identify them reliably among the many faint infrared sources that populate the sky. As infrared surveys continue and new sensitive instruments come online, the number of individually characterized rogues will grow, perhaps reaching hundreds or thousands of objects with measured properties that allow us to begin classifying them into different categories and understanding their diversity. These portraits of worlds we cannot see in visible light remind us that the universe contains vast numbers of objects that challenge our definitions and our detection capabilities, worlds that exist in the darkness between the stars, cooling slowly over billions of years, preserving in their properties the memory of their violent ejection from the systems where they were born. The question of how rogue planets come to exist, how worlds that presumably formed in orbit around stars end up wandering alone through the galaxy, lies at the heart of understanding these objects and their implications for planetary system architecture. The answer, we have come to realize, involves some of the most violent and dramatic processes in planetary system evolution. Episodes of gravitational chaos, during which the stable orbital configurations we see in mature systems like our own had not yet been established. The dominant mechanism for rogue planet production appears to be gravitational scattering, a process that occurs when planets in a forming or young planetary system interact gravitationally with one another, their mutual gravitational attractions perturbing their orbits until the system becomes dynamically unstable. In such situations, planets can be scattered onto highly elliptical orbits, ejected from the system entirely, or even collided together in devastating impacts that reshape or destroy them. This process likely played a major role in the early evolution of our own solar system and of most planetary systems throughout the galaxy. To understand how gravitational scattering leads to ejection, we need to consider the basic physics of orbital dynamics in systems with multiple massive bodies. When a planet orbits alone around a star, its orbit is stable and predictable, following an elliptical path that, barring external perturbations, could continue unchanged for the lifetime of the star. But when multiple planets orbit the same star, especially if those planets have significant masses and orbits that bring them relatively close to one another, the situation becomes far more complex and potentially unstable. Each planet exerts gravitational forces on every other planet, and these forces, though small compared to the star's gravity, accumulate over time and can gradually alter orbital configurations. If the planets are well separated and their orbits are nearly circular, these perturbations typically remain small, causing slow precession of orbital orientations, but not leading to dramatic changes in orbital radii or eccentricities. The solar system's planetary orbits appear to have settled into such a stable configuration after the chaos of its youth subsided, with the planets spaced far enough apart that their mutual interactions cause only gradual, predictable changes. But if planets are more closely spaced, or if their orbits are more eccentric, allowing closer approaches, the perturbations can grow stronger and can enter a regime where they reinforce one another, driving orbital eccentricities higher and bringing planets into even closer encounters. This positive feedback can lead to dramatic instability on timescales much shorter than the system's age. Computer simulations of such unstable configurations show that once instability sets in, the system typically reorganizes itself within a few 100,000 to a few million years, with some planets settling into stable orbits, while others are scattered to large distances or ejected completely. The outcome of these scattering events depends on the energy and angular momentum involved in each close encounter. When two planets approach one another closely, they exchange energy and angular momentum through their gravitational interaction, with one typically gaining energy and moving to a more distant orbit, while the other loses energy and falls inward toward the star. But if a planet gains enough energy in such an encounter, it can acquire more than enough velocity to escape the star's gravitational well entirely, becoming unbound and flying off into interstellar space as a rogue planet. The probability of ejection depends on several factors. The masses of the interacting planets, with more massive planets more effective at scattering less massive ones. The architecture of the system, with more compact configurations leading to more frequent close encounters, and the presence of any gas giant planets whose large masses make them particularly effective at ejecting smaller worlds. Systems with multiple gas giants appear particularly prone to instability, because the gravitational interactions between massive planets can become very strong, leading to dramatic orbital rearrangements. Evidence for such early instability episodes comes from several sources. The orbits of the giant planets in our own solar system show patterns that suggest they underwent significant migration in the past, with Jupiter perhaps moving inward from a more distant initial orbit, and the ice giants, Uranus and Neptune, likely forming closer to the Sun before being scattered outward to their current locations. The Late Heavy Bombardment, an episode roughly 4 billion years ago, during which the inner solar system experienced intense impacts, may have been triggered by reorganization of the giant planets' orbits that destabilized populations of smaller bodies throughout the system. Computer simulations of planetary system formation routinely produce rogue planets as a natural byproduct of the formation process. These simulations typically begin with a young star surrounded by a protoplanetary disk containing numerous planetary embryos, objects with masses ranging from Earth mass to several Jupiter masses. As these embryos gravitationally interact with one another and with the gas disk, they merge to form larger planets, while some are ejected from the system. The simulation suggests that on average, each planetary system might eject one or more planets during its first 100 million years, consistent with the observed abundance of rogue planets in the galaxy. This picture of planet formation as an inherently violent and chaotic process, with stable planetary systems emerging only after a shakedown period during which weaker members are ejected, represents a significant evolution in our thinking about how solar systems form. The rogue planets wandering the galaxy serve as fossil evidence of this violence, each one a world that lost the gravitational battle for survival and was cast into the darkness, carrying with it the story of its birth system's tumultuous youth. The detailed physics of planetary ejection involves some of the most challenging problems in celestial mechanics. Situations where multiple massive bodies interact gravitationally in ways that can only be solved through detailed numerical simulations rather than through analytical mathematics. These problems fall into the category of what physicists call the n-body problem, the question of how to predict the future motions of n objects that all gravitationally attract one another, a problem that has no general solution for n greater than 2, and that requires computational approaches for realistic systems. At the heart of planetary ejection lies the three-body encounter, a situation in which two planets approach one another closely while both orbit the same star. During such an encounter, the three objects, the two planets and the star, form a temporary bound system whose dynamics depend sensitively on the initial conditions. The planets' masses, their relative velocities, the angle of their approach, and the distance of closest approach. Small changes in any of these parameters can lead to dramatically different outcomes, a characteristic sensitivity that makes planetary dynamics both fascinating and difficult to predict. During a close encounter between two planets, their mutual gravitational attraction creates forces that change each planet's velocity relative to the star. The planet that passes behind the other, in their shared motion around the star, tends to gain energy, its velocity increasing as it is gravitationally accelerated by its partner. The planet that passes ahead tends to lose energy, its velocity decreasing as it exerts an equal and opposite gravitational force on its partner. This energy exchange, combined with the complex trajectories that develop during the close approach, can radically alter both orbits. For ejection to occur, one planet must gain sufficient energy that its velocity relative to the star exceeds the escape velocity at its position, the minimum velocity needed to leave the star's gravitational well entirely. For a planet initially in a circular orbit at Jupiter's distance from a Sun-like star, the escape velocity equals roughly 18 kilometers per second, about 40% more than the orbital velocity of 13 kilometers per second. A close encounter that increases the planet's velocity by at least this amount will send it on an unbound trajectory toward interstellar space. The energy required for ejection must come from somewhere, and by conservation of energy, it must be extracted from the kinetic or potential energy of the other planets in the system. Typically, when one planet is ejected with energy substantially exceeding the escape velocity, other planets in the system move to more tightly bound orbits, their orbital radii decreasing to compensate for the energy given to the ejected world. This energy exchange means that systems that eject planets often become more compact, with the remaining planets orbiting closer to the star than they did before the instability. The angular momentum of the system also constrains what outcomes are possible. Total angular momentum must be conserved in the absence of external torques, so when a planet is ejected, it typically carries away a significant fraction of the system's angular momentum. This can be compensated by increasing the orbital angular momentum of the remaining planets, either through increasing their orbital radii or through increasing their orbital eccentricities. The requirement of angular momentum conservation means that not every unstable configuration can lead to clean ejections. Sometimes the system must reorganize through collisions or through scattering to wider orbits, rather than through complete removal of planets. Computer simulations that follow the trajectories of planets in unstable systems show that the typical ejection velocity for a rogue planet exceeds the escape velocity by a substantial margin, often by factors of 2 or more. This means that rogue planets do not barely escape their birth systems. Rather, they are flung violently into interstellar space with velocities of 20, 30, or even 50 kilometers per second relative to their parent stars. These velocities are comparable to the orbital velocities of stars around the galactic center, meaning that ejected planets become participants in the galaxy's overall rotation rather than remaining associated with their birth systems. The timing of ejection events also matters for understanding the rogue planet population. Most ejections probably occur early in a planetary system's history, during the first few million to perhaps 100 million years, when the system is still settling into its final configuration and when close encounters between planets remain relatively probable. After this shakedown period, remaining planets have typically settled into stable orbits that prevent further close encounters, reducing the ejection rate to nearly zero. This means that most rogue planets in the galaxy are old, having wandered alone for billions of years, though a minority are young, recently ejected from systems still undergoing dynamical evolution. Understanding these ejection physics helps us interpret the properties of observed rogue planets. The fact that ejected planets typically leave with velocities well above escape velocity explains why most rogues move quickly through the galaxy and why their probability of being recaptured by another star is very low. The preference for ejecting less massive planets in encounters with more massive ones explains why we might expect terrestrial mass rogues to outnumber gas giant mass rogues, though this prediction remains uncertain due to other factors in the ejection process. The physics of exile, these complex gravitational interactions, that transform orbiting planets into wandering exiles, represents one of the fundamental processes shaping planetary system architecture. Every stable system we observe, including our own, likely passed through an unstable phase during which some fraction of its original planetary population was lost to interstellar space, leaving behind the survivors whose orbits proved stable enough to persist through billions of years of subsequent evolution. While gravitational scattering appears to be the dominant mechanism for producing rogue planets, theoretical work has identified an alternative formation pathway that might contribute significantly to the rogue planet population, particularly at the low-mass end of the mass range. This mechanism involves the formation of planetary mass objects through the same basic process that forms stars, direct gravitational collapse of regions within molecular clouds, but occurring at mass scales too small to sustain hydrogen fusion, and thus producing objects that are planets by mass, but that never belong to any planetary system. The process of star formation begins when regions within giant molecular clouds, vast accumulations of cold gas and dust that permeate the galaxy, become gravitationally unstable and begin to collapse under their own weight. As these regions contract, they fragment into smaller clumps, each of which can potentially form a star if it contains sufficient mass and if it can radiate away the gravitational energy released during contraction. The minimum mass required to form an object that will eventually become a hydrogen-burning star equals roughly 0.08 solar masses, or about 80 Jupiter masses, set by the requirement that the core must become hot and dense enough for nuclear fusion to ignite. But the fragmentation process that operates in collapsing molecular cloud regions does not stop at this minimum stellar mass. Under favorable conditions, particularly in regions where turbulence or external compression provides extra support against gravity, the fragmentation can continue to smaller and smaller mass scales, potentially producing objects well below the hydrogen-burning limit. These substellar objects, if they form through the same gravitational collapse process as stars, share more in common with stars than with planets, despite their planetary masses. Observations of star-forming regions have revealed populations of very low-mass objects that might have formed through this fragmentation process. These objects, sometimes called free-floating planetary mass objects, or isolated planetary mass objects to distinguish them from planets formed in disks, have masses ranging from a few Jupiter masses up to roughly 13 Jupiter masses. The approximate threshold above which objects can burn deuterium and are classified as brown dwarfs. Their existence in young star-forming regions, often far from any nearby star, suggests formation through cloud fragmentation rather than through ejection from planetary systems. The distinction between rogue planets formed through ejection and planetary mass objects formed through fragmentation matters for several reasons. Objects formed through fragmentation would never have been part of a planetary system, and thus would not carry information about planetary system dynamics or evolution. They would likely lack moons, since the circumstellar disks that typically accompany forming planets and that provide the material for satellite formation would be much smaller or absent entirely for such low-mass objects. Their compositions might differ from ejected planets, reflecting the composition of the molecular cloud material from which they formed rather than the composition of a specific protoplanetary disk. The boundary between star formation and planet formation, between gravitational collapse and core accretion in a disk, appears to be gradual rather than sharp, with both processes potentially operating at intermediate masses and perhaps producing objects with similar properties through different pathways. This makes it challenging to determine, for any individual low-mass object discovered in isolation, whether it formed as a planet and was ejected or formed through direct collapse in a molecular cloud. The two populations might be distinguishable statistically through their spatial distributions, with fragmentation-formed objects more tightly associated with molecular clouds and star-forming regions. But for individual objects, the formation mechanism often remains ambiguous. Some theoretical models suggest that fragmentation might be the dominant formation mechanism for the lowest mass free-floating objects, those below perhaps 5 Jupiter masses, while gravitational ejection dominates at higher masses. The reasoning is that very low-mass objects are difficult to eject from planetary systems because they interact weakly with more massive planets and thus are less likely to gain the energy needed for escape. Meanwhile, cloud fragmentation can more easily produce very low-mass objects if conditions allow fragmentation to continue to small scales. This would imply a transition in the rogue planet population, with massive rogues primarily ejected from systems and low-mass rogues primarily formed through fragmentation. The question of how common fragmentation formed planetary mass objects might be relative to ejection-formed rogues remains open. Some estimates suggest that fragmentation might contribute 10 to 20% of the total rogue planet population, with the remainder being ejected from systems. Other estimates suggest fragmentation might be more important, perhaps contributing equally to ejection at certain mass ranges. The uncertainties arise from our incomplete understanding of both the fragmentation process at low masses and the efficiency of planetary ejection in different system architectures. Future observations might help distinguish between these formation pathways by searching for differences in the properties of free-floating objects found in different environments. Objects in young star-forming regions, where fragmentation would be ongoing, might show different age and temperature distributions than objects in the field, where most would be ejected planets that formed earlier. Detailed studies of individual objects' compositions and kinematics might reveal whether they formed in the molecular cloud environment or in protoplanetary disks. The possibility that some rogue planets never belonged to planetary systems, that they formed as star formation's castaways through a process that simply did not accumulate enough mass to create a star, adds another layer of complexity to our understanding of these objects. It reminds us that the universe's creativity in forming objects spans a continuum from stars to brown dwarfs to planets to smaller bodies, with multiple formation pathways operating across this range, and with the boundaries between categories more fluid than our desire for classification might prefer. Once a planet has been ejected from its birth system or formed in isolation, it embarks on a journey that will last for the remaining lifetime of the galaxy. Billions or even trillions of years of wandering through the near vacuum between the stars, following an orbit around the galactic center that will carry it through diverse environments, but that will almost certainly never bring it close enough to another star to alter its trajectory significantly or to allow its capture into a new planetary system. The typical rogue planet, ejected from a system in the galactic disk, begins its journey with a velocity relative to its parent star of perhaps 20 to 50 kilometers per second, as we discussed earlier. This velocity vector, combined with the parent star's own velocity around the galactic center, determines the rogue's initial galactic orbit. Because the escape velocity from the galaxy at the sun's position equals roughly 550 kilometers per second, far higher than any plausible ejection velocity, the rogue remains gravitationally bound to the galaxy itself, becoming a permanent resident of the galactic stellar population even though it no longer orbits any particular star. The rogue planet's orbit around the galactic center follows the same basic physics as a planet's orbit around a star, though the gravitational field it experiences comes not from a single central mass, but from the distributed mass of all the stars, gas and dark matter within its orbital radius. For a rogue in the solar neighborhood, located roughly 26,000 light-years from the galactic center, the orbital period around the galaxy equals approximately 225 million years, the same as the Sun's galactic year. The rogue will complete roughly 40 to 50 of these galactic orbits during the remaining lifetime of the galaxy, before the Milky Way's merger with Andromeda in 4 to 5 billion years disrupts the current orbital structure. During its journey around the galaxy, the rogue planet encounters a constantly changing environment as it moves through different regions of the galactic disk. When passing through spiral arms, regions of enhanced stellar density and active star formation, the rogue experiences a slightly stronger gravitational field and higher probability of close encounters with other objects. Though even in spiral arms, the space between stars remains so vast that actual collisions or close approaches remain extraordinarily rare. When passing through the interarm regions, the rogue finds itself in more isolated space, with greater distances to the nearest stars and less frequent perturbations to its orbit. The question of how a rogue planet's orbit evolves over billions of years depends on these weak perturbations from passing stars and from the galaxy's overall gravitational field. Each stellar encounter, even a distant one, exerts a small gravitational force on the rogue, slightly changing its velocity and therefore its orbit. Over millions of encounters spanning billions of years, these small changes accumulate, causing the rogue's orbit to undergo what physicists call a random walk through orbital parameter space, with its distance from the galactic center and its velocity direction changing gradually and unpredictably. Computer simulations that follow rogue planets through billions of years of galactic orbital evolution show that most rogues remain in roughly the same region of the galaxy, where they were ejected, moving around the galactic center in orbits that carry them up and down through the galactic disk, but that don't change their average distance from the center dramatically. A planet ejected in the solar neighborhood, 26,000 light-years from the galactic center, will typically still be found within a few thousand light-years of that radius several billion years later, though its exact position and velocity will have changed unpredictably due to accumulated perturbations. The probability that a rogue planet will encounter another star closely enough for the encounter to significantly affect its trajectory remains extremely small throughout its lifetime. The typical separation between stars in the solar neighborhood equals roughly 5 light-years, or about 30 trillion miles, vast compared to the size of planetary systems, but small compared to the scale of the galaxy itself. For a rogue to pass within a few hundred astronomical units of another star, close enough for the star's gravity to substantially perturb the rogue's galactic orbit, requires an alignment that occurs perhaps once every several billion years on average. And even then, the encounter would typically scatter the rogue into a different galactic orbit rather than capturing it into orbit around the star. True capture of a rogue planet into a new planetary system appears to be extraordinarily rare, requiring an encounter that not only brings the rogue close to a star, but that also dissipates enough of the rogue's kinetic energy relative to the star that it becomes gravitationally bound. This energy dissipation might occur through a three-body interaction, in which the rogue encounters a binary star system and is captured through a complex gravitational dance with the two stars, or through interaction with the star's planetary system, if one exists. But the combination of geometric requirements for a close encounter and dynamical requirements for energy dissipation makes capture probability very low, with typical rogues having perhaps a 1% chance or less of being captured over the galaxy's remaining lifetime. This means that the vast majority of rogue planets, once ejected or formed, remain rogues forever, wandering the galaxy for billions of years without ever experiencing the warmth of a nearby star again, without ever rejoining the orbital dance of a planetary system. Their journeys are journeys of ultimate isolation, paths that carry them through diverse galactic environments and past countless stars, but that almost never bring them close enough to any other object to alter their fundamental status as wanderers. The long journey between stars becomes an eternal journey, a trajectory that will continue until the galaxy itself undergoes dramatic reorganization through merger, or until the universe ages so much that the very concept of galactic structure loses meaning. Despite the low probability of capture that we just explored, the possibility that some rogue planets might be captured into new planetary systems, returning from exile to rejoin the orbital architecture of a stellar system, raises intriguing questions about the origins of unusual objects in known systems and about whether our own solar system might host captured rogues that we have not yet recognized as such. The physics of planetary capture provides insights into what kinds of systems might successfully capture rogues and what signatures such captured objects might display. The fundamental challenge in capturing a rogue planet lies in energy conservation. When a rogue approaches a star on an unbound trajectory, its kinetic energy relative to the star exceeds the gravitational binding energy available at its closest approach distance. For the rogue to become bound, it must lose energy somehow, transferring kinetic energy to another object or radiating it away through some mechanism. Without such energy loss, the rogue will simply swing past the star on a hyperbolic trajectory and continue into interstellar space. Its velocity changed, but its status as a rogue unchanged. The most efficient mechanism for capture involves three-body interactions, in which the rogue encounters not a single star, but a binary star system, two stars orbiting one another. In such encounters, the complex gravitational dance between the rogue and the two stars can result in the rogue losing energy to the binary's orbital motion, with the binary becoming slightly more tightly bound, while the rogue becomes captured into a wide orbit around the binary. This mechanism, studied extensively through computer simulations, can capture rogues with significant efficiency if the encounter geometry is favorable, and if the binary's orbital properties match the rogue's approach velocity appropriately. The resulting captured planet typically finds itself in a highly elliptical orbit with a semi-major axis much larger than those of planets that formed in the system, often hundreds or thousands of astronomical units from the central star or stars. These wide orbits distinguish captured planets from native-born planets and might provide an observational signature that could identify captured rogues in known planetary systems. Additionally, captured planets might have orbital inclinations that differ significantly from the system's overall plane, another signature of their capture origin rather than formation within the system's protoplanetary disk. Some planetary systems in our galaxy do host planets in very wide orbits, and for at least some of these, capture from the free-floating population might be a plausible origin. The system containing the star HD 106906, for instance, includes a planet roughly 11 times Jupiter's mass orbiting at a distance of 738 astronomical units, far beyond the expected outer edge of the system's protoplanetary disk. While this planet might have formed closer to the star and been scattered outward through gravitational interactions, capture from the free-floating population offers an alternative explanation for its unusual properties. In our own solar system, the question of whether we host any captured rogue planets focuses attention on the outer solar system's unusual objects and on the hypothetical planet 9, a planet that might exist at enormous distances from the Sun based on the orbital clustering of certain trans-Neptunian objects. If planet 9 exists, with estimated mass of roughly 5 to 10 Earth masses and orbital distance of perhaps 400 to 800 astronomical units, its properties would be consistent with either formation in the outer solar system, followed by scattering to wide orbits, or with capture from the free-floating population during the Sun's early history, when it resided in its birth cluster. The Sun formed in a cluster containing hundreds or thousands of other stars, a dense environment where stellar separations were much smaller than they are in the current solar neighborhood. In such environments, the probability of a rogue planet passing close enough to a young stellar system to be captured increases substantially, perhaps high enough that a significant fraction of stars might have captured rogues. As the birth cluster dispersed over tens of millions of years, most stars, including the Sun, moved apart and now exist in the relatively isolated environment we see today, but any planets captured during the cluster phase would have remained bound as the cluster dissolved. Some researchers have proposed that captured rogues might explain certain unusual properties of solar system objects. The planet Uranus, for instance, has an axial tilt of 98 degrees, meaning it essentially orbits the Sun on its side, with its rotational pole lying nearly in its orbital plane. While this extreme tilt is typically explained through a giant impact during the late stages of the solar system's formation, some models have explored whether Uranus might instead be a captured rogue planet whose initial orbital orientation was not aligned with the solar system's plane. Most evidence favors the impact scenario, but the capture hypothesis illustrates how rogues might leave unusual signatures if they are incorporated into established planetary systems. Looking forward, the search for captured rogue planets in known exoplanetary systems offers an interesting observational program for current and future telescopes. Direct imaging surveys searching for planets in wide orbits around nearby stars might reveal populations of captured objects distinguishable from scattered natives through statistical analysis of their orbital properties and abundance. If captured rogues are common, we might expect to find them preferentially around stars that formed in denser clusters where capture probabilities were higher, and we might expect their orbital distributions to differ from those of planets that formed in situ. The possibility that rogues can return, that planets exiled from their birth systems might sometimes find new homes around different stars, adds a dynamic element to our picture of planetary system evolution. While most rogues remain wanderers forever, a small fraction might rejoin the orbital dance, bringing with them properties that reflect their formation environments and ejection histories, potentially carrying even biological material if they hosted life during their exile. The captured rogues would become ambassadors between systems, connecting the evolutionary histories of separate planetary systems through their transfer from one to another, writing stories of exile and return into the architecture of the galaxy's planetary census. Understanding which types of planets are most likely to be ejected from their birth systems and which system architectures most efficiently produce rogues helps us interpret the observed rogue planet population and make predictions about what future surveys might find. The answer to these questions lies in the detailed dynamics of planet-planet scattering and in the relationship between planetary system architecture and long-term stability. Computer simulations of unstable planetary systems reveal clear patterns in ejection outcomes that depend on the masses and initial orbital configurations of the planets involved. In systems containing planets of different masses, the less massive planets tend to be ejected preferentially, while more massive planets tend to remain bound, moving to more tightly bound orbits that compensate for the energy given to the ejected worlds. This mass-dependent outcome arises from the basic physics of gravitational scattering. More massive planets exert stronger gravitational forces and thus can more effectively accelerate less massive planets to escape velocity. A typical unstable system containing both gas giants and terrestrial planets, for instance, might eject most or all of its terrestrial planets while retaining its gas giants in modified orbits. The gas giants, with masses hundreds of times those of terrestrial worlds, can easily impart escape velocities to Earth-mass planets during close encounters, while terrestrial planets have much more difficulty ejecting gas giants due to their lower masses. This suggests that the rogue planet population might be dominated by low-mass worlds, with more terrestrial planets than gas giants wandering the galaxy, despite the fact that gas giants were historically easier to detect. However, this simple mass-dependent picture becomes more complex when we consider that not all planetary systems have the same architecture. Systems with multiple gas giants can experience gas giant on gas giant scattering, with one giant ejecting another if their orbital configuration becomes unstable. In fact, some of the most violent ejections, those producing rogues with the highest velocities relative to their parent stars, occur when two gas giants interact strongly, with one gaining enough energy to leave its speed substantially exceeding escape velocity. This suggests that gas giant rogues should exist in significant numbers despite the general preference for ejecting low-mass planets. The initial architecture of a planetary system, the number of planets it contains and their orbital separations, strongly influences its stability and therefore its likelihood of producing rogues. Systems with planets closely spaced in orbital radius become unstable more readily than systems with widely separated planets, because closely spaced planets experience stronger mutual gravitational perturbations. There appears to be a critical spacing, often expressed in terms of mutual Hill radii, the gravitational sphere of influence, that each planet maintains against perturbations from neighbours, below which systems become very likely to experience instability on timescales short compared to their ages. Many of the extrasolar planetary systems discovered to date appear to have architectures that place them close to this stability boundary, with planets spaced just widely enough to remain stable, but not so widely separated that additional planets could fit between them. This configuration, sometimes called packed systems, might represent the natural outcome of planet formation followed by orbital instability and ejection, with the remaining planets occupying the most tightly packed configuration that remains long-term stable. If so, then most planetary systems might have ejected planets in their past, with the number of ejections depending on how many planets initially formed and how closely spaced they were. The presence of gas giants in a planetary system appears to be a key predictor of whether ejections occurred, because gas giant gravitational interactions drive the most dramatic instabilities. Systems without gas giants, containing only terrestrial or ice giant-sized planets, can certainly experience instability and ejections, but the energy scales involved are typically smaller and the ejection velocities lower. Systems with multiple gas giants, conversely, often experience violent instability episodes during which one or more giants are ejected and the remaining giants settle into widely separated, eccentric orbits. Our own solar system provides an example of a system that likely experienced significant orbital rearrangement, but that apparently did not eject any giant planets. The NICE model of solar system evolution, named after the French city where it was developed, proposes that the giant planets formed in a more compact configuration than they occupy today, and that their orbits became unstable roughly 500 million years after the solar system's formation, leading to a period of planet migration and scattering of smaller bodies. During this episode, Jupiter moved inward slightly, Saturn, Uranus and Neptune moved outward, and numerous smaller bodies were ejected or scattered into the Oort cloud, but the four giants remained bound, possibly due to their particular mass ratios and orbital relationships. However, some simulations of solar system formation suggest that the early solar system might have contained one or more additional planets that were ejected during the instability phase, perhaps ice giants, comparable to Uranus or Neptune, that formed between the current orbits of the giant planets and were removed through scattering. The existence or non-existence of such ejected solar system siblings remains an open question, one that might be addressed through future observations if we could detect solar system composition rogues in the local neighbourhood that might have originated from our system. Looking at the broader galactic population, the architecture of ejection predicts that we should find a mass distribution of rogues that reflects both the typical planetary system mass distribution and the mass-dependent efficiency of ejection. If most systems form more low-mass planets than high-mass planets, and if low-mass planets are preferentially ejected, then the rogue population should be heavily weighted toward terrestrial masses. Future surveys capable of detecting Earth mass rogues will test this prediction and will help us understand typical planetary system architectures by revealing the population of planets that were removed from systems through dynamical instability. The question of whether life could exist on a rogue planet, a world forever divorced from stellar warmth and bathed only in the faint light of the distant stars, seems at first to have an obvious answer. No, life as we understand it requires energy sources and liquid water, neither of which would seem available on a frozen world drifting through interstellar space. But careful consideration of the energy sources available to rogue planets and of the environments beneath their frozen surfaces reveals that the situation is more nuanced and that habitability, at least in principle, cannot be ruled out for certain types of rogue worlds. The fundamental requirement for life as we know it is liquid water, the solvent in which biochemical reactions occur and the medium that allows the complex molecular interactions necessary for metabolism, reproduction, and evolution. On Earth, liquid water exists because our distance from the Sun places us in the habitable zone, the range of orbital radii where temperatures allow water to remain liquid at the surface. A rogue planet has no star to provide external heating, so any liquid water must be maintained through internal heat sources and through insulation that prevents that heat from escaping too rapidly to space. For a rogue terrestrial planet, several internal heat sources might maintain habitable conditions beneath the surface, even without stellar heating. Radioactive decay of long-lived isotopes, primarily uranium-238, thorium-232, and potassium-40, produces heat in planetary interiors that can persist for billions of years, providing a steady energy flow of roughly 0.1 watts per square meter for an Earth-sized world. While this is tiny compared to the roughly 240 watts per square meter that Earth receives from the Sun, it accumulates beneath the surface and can maintain elevated temperatures at depth if insulation is sufficient. The insulation necessary to trap this geothermal heat and maintain liquid water could come from a thick layer of surface ice that forms when the planet is ejected into interstellar space and its oceans freeze. Water ice is an excellent insulator, particularly when it contains trapped gases or when it forms in multiple layers with different properties. A global ice shell, several kilometers thick, could reduce heat loss sufficiently that geothermal heat maintains liquid water at the ice-rock interface, creating an environment broadly similar to the subsurface oceans believed to exist beneath the ice shells of Jupiter's moon Europa and Saturn's moon Enceladus. But surface ice alone might not provide sufficient insulation for many rogue Earth scenarios. Additional insulation could come from a thick atmosphere, particularly a hydrogen atmosphere, if the planet managed to capture hydrogen from the protoplanetary disk during formation, or if it generated hydrogen through chemical processes. Hydrogen is an extremely effective greenhouse gas, and a hydrogen atmosphere with pressure even a few times Earth's atmospheric pressure could warm the surface ice significantly through greenhouse effect, reducing heat loss and helping maintain subsurface liquid water even with modest geothermal heat flow. Computer models exploring rogue planet habitability have identified parameter ranges where subsurface oceans could remain liquid for billions of years. An Earth-mass planet with a 5 to 10 kilometer thick ice shell, a hydrogen atmosphere with pressure several times Earth's, and typical radioactive element abundances could maintain a layer of liquid water beneath the ice at temperatures above freezing for timescales comparable to the current age of Earth. The habitable zone would lie at the base of the ice shell, where geothermal heat from below meets cold ice from above, possibly creating a kilometers-thick layer of liquid water in direct contact with the rocky sea floor. The presence of large moons orbiting a rogue planet could substantially enhance habitability prospects through tidal heating. If a rogue planet ejected from its birth system retained one or more substantial moons, the tidal forces those moons exert on the planet and that the planet exerts on the moons could generate significant additional heat through tidal flexing, just as tidal forces from Jupiter heat Europa and Enceladus. This tidal heat would add to the radioactive heat, potentially allowing a rogue planet-moon system to maintain more extensive subsurface oceans or warmer surface conditions than would otherwise be possible. The energy available to life on a rogue planet would be limited compared to solar-powered ecosystems on Earth, but not impossibly so. Earth hosts ecosystems in deep ocean hydrothermal vents that receive no sunlight and that derive all their energy from chemical reactions between minerals in the Earth's crust and seawater. These chemosynthetic ecosystems prove that life can exist entirely independent of stellar energy, deriving the energy it needs from geological processes. A subsurface ocean on a rogue planet in contact with a rocky seafloor could support similar chemosynthetic ecosystems, with organisms deriving energy from reactions between rock and water, from dissolved chemicals, or from thermal gradients. The possibility that rogue planets might host life has profound implications for thinking about the distribution of life in the galaxy. If habitable conditions can exist on rogues, then the total habitable volume in the galaxy might be much larger than previously thought, not restricted to the narrow habitable zones around stars, but extending throughout interstellar space wherever rogues with suitable properties drift. The number of potentially habitable environments might approach or exceed the number of stars, with trillions of possible abodes for life hidden in the darkness between stellar systems. Detecting life on a rogue planet would be extraordinarily challenging, requiring not just finding the rogue itself, already a difficult task, but then characterizing its atmospheric composition or somehow probing beneath its icy surface to search for biosignatures. No current or planned mission has such capability, but future generations of instruments might search for atmospheric biosignatures on rogues detected through microlensing or direct imaging. The discovery of life on a rogue planet would revolutionize our understanding of life's requirements and would suggest that the universe might be far more alive than even optimistic estimates suggest, with life flourishing in darkness across the full expanse of every galaxy. The atmospheres of rogue planets play a crucial role in determining their potential habitability and their long-term thermal evolution, serving as insulating blankets that can trap internal heat and maintain surface temperatures substantially above what would exist in vacuum. The composition, pressure, and structure of a rogue planet's atmosphere depend on its formation history, its mass, and the details of its ejection or isolation, creating a diverse range of possible atmospheric states. For a gas giant rogue, the atmosphere dominates the entire structure of the planet, with the hydrogen-helium envelope that constitutes most of the planet's mass gradually transitioning to liquid and then to exotic metallic states at depth. The ejection of such a planet from its birth system would not significantly affect this atmospheric structure, though the coldest upper layers might undergo changes as the planet cools in the absence of stellar heating. Methane, ammonia, and water that were gaseous in the upper atmosphere when the planet orbited a star would condense into ices and precipitate downward, leaving the observable upper atmosphere dominated by hydrogen and helium, with trace amounts of more volatile compounds. The effective temperature of a rogue gas giant, the temperature its surface would need to be to radiate away its internal heat flow, depends on the planet's age and mass. Young rogue gas giants, those ejected within the last few 100 million years, might have effective temperatures of 500 to 1000 Kelvin, warm enough to maintain complex atmospheric chemistry and to produce observable signatures in the near-infrared. As the planet ages and its internal heat slowly dissipates through radiation to space, the effective temperature decreases, dropping to perhaps 100 Kelvin after a few billion years, and continuing to decline toward the cosmic microwave background temperature of 3 Kelvin over timescales much longer than the current age of the universe. For terrestrial rogue planets, the atmospheric evolution follows a very different trajectory. A planet ejected from the habitable zone of its parent star, initially possessing an Earth-like atmosphere of nitrogen, oxygen, carbon dioxide, and water vapor, would experience catastrophic atmospheric collapse as it cooled in interstellar space. Water vapor would condense first, forming global cloud cover and then precipitating as snow that would accumulate into kilometer-thick ice deposits over perhaps 1 million years. Next, carbon dioxide would freeze, condensing out of the atmosphere as dry ice that would cover the water ice with another layer of solid CO2. Eventually, even nitrogen and oxygen would begin to freeze at temperatures below 70 Kelvin, though this would take longer due to their lower freezing points. The result of this atmospheric collapse would be a planet with most of its original atmosphere frozen onto its surface as layered ices, with only a thin residual atmosphere of the most volatile compounds remaining in gaseous form. But this is where the story becomes interesting for habitability, because the frozen atmosphere itself becomes part of the insulating blanket that can trap geothermal heat and potentially maintain subsurface liquid water. The layers of ice, each with different thermal properties, create a complex thermal structure in which temperature increases with depth beneath the surface, potentially reaching the melting point of water at the base of the ice shell where it contacts the rocky interior. The most effective atmospheric composition for maintaining rogue planet habitability appears to be a thick hydrogen atmosphere, either primordial hydrogen captured during the planet's formation or molecular hydrogen generated through chemical weathering of rocks. Hydrogen's low molecular weight gives it excellent insulating properties, and its ability to absorb and re-emit infrared radiation makes it an effective greenhouse gas. Models suggest that a rogue Earth mass planet with a hydrogen atmosphere at 1 to 10 bars pressure, roughly Earth's atmospheric pressure to 10 times that pressure, could maintain surface ice temperatures of 200 Kelvin or higher, even with only geothermal heating, warm enough that the base of the ice shell would remain liquid. The retention of such a hydrogen atmosphere over billions of years requires that the planet's escape velocity be sufficient to prevent atmospheric loss to space. Earth's relatively low escape velocity, 11 kilometers per second, makes it difficult for Earth to retain primordial hydrogen because hydrogen molecules at typical atmospheric temperatures have thermal velocities approaching escape velocity. But a planet with somewhat higher mass, perhaps 2 or 3 Earth masses, would have escape velocities high enough to retain hydrogen atmospheres over geological timescales, making these super-Earth rogues potentially more habitable than Earth mass rogues. The vertical structure of a rogue planet atmosphere, how temperature and pressure vary with altitude above the surface or with depth below the visible cloud layers, determines the wavelengths at which the planet emits most strongly and therefore its detectability. For a gas giant rogue, the pressure level in the atmosphere that we observe when we look at the planet in the infrared corresponds to a specific temperature, typically in the range where the atmospheric opacity becomes large enough to block our view of deeper layers. This temperature-pressure relationship creates the effective temperature we observe and determines the planet's color and spectral properties. For terrestrial rogues with thin residual atmospheres, the observable surface might be the solid ice layer itself rather than a gaseous atmosphere, with infrared observations revealing the temperature and composition of the ice. Future infrared spectroscopy of rogue terrestrial planets might be able to determine whether their surfaces are covered with water ice, carbon dioxide ice, or nitrogen ice, providing clues to their formation environments and ejection histories. The presence of unexpected atmospheric gases, methane for instance, might even serve as biosignature gases if they can only be maintained against photochemical destruction through biological processes, though interpreting such biosignatures on rogues would be extremely challenging without better understanding of rogue planet atmospheric chemistry. The atmosphere of a rogue planet, whether thick and gaseous or thin and frozen, serves as the interface between the planet's interior heat and the cold of interstellar space, mediating the energy flow that determines whether habitable conditions can exist and mediating the planet's detectability through their effects on the thermal emission spectrum. Understanding rogue planet atmospheres requires combining atmospheric physics developed for solar system planets with extreme extrapolation to conditions that have no solar system analogue, creating opportunities for atmospheric science to explore entirely new regimes of temperature, pressure, and composition that might characterize countless worlds hidden in the galaxy's dark spaces. The next generation of rogue planet searches will push detection capabilities down into the terrestrial planet mass range, searching specifically for wandering Earths, rocky worlds that might have once orbited in habitable zones before being ejected into the interstellar dark. These searches, enabled by new space telescopes and improved detection algorithms, promise to reveal whether the rogue planet population includes large numbers of small worlds and whether any of these worlds might have retained conditions suitable for life, despite their exile from stellar warmth. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-20s, represents the most capable rogue planet detection facility that will be available in the coming decade. Roman will conduct an extensive microlensing survey toward the galactic bulge, monitoring hundreds of millions of stars with the sensitivity and temporal coverage needed to detect lensing events caused by Earth mass and smaller rogue planets. The space-based location provides crucial advantages over ground-based surveys, continuous monitoring without day-night cycles, superior image quality without atmospheric distortion, and access to wavelengths that Earth's atmosphere blocks. Roman's microlensing survey is predicted to detect dozens to potentially hundreds of terrestrial mass rogue planets during its primary 5-year mission, depending on the actual abundance of such objects. Each detection will add a data point to our understanding of the rogue planet mass distribution, helping answer whether terrestrial rogues outnumber gas giant rogues, as some formation models predict. The detections will also provide information about the spatial distribution of rogues, revealing whether they cluster near star-forming regions or distribute uniformly throughout the galactic disk. Beyond microlensing, future infrared surveys from space will search for the thermal emission of young rogue planets that still retain significant heat from their formation. The James Webb Space Telescope, already operating in orbit, has the sensitivity to detect and characterize relatively warm rogues within a few hundred light-years of Earth, though its small field of view limits its ability to conduct wide-area searches. Future dedicated infrared survey missions might conduct more comprehensive searches, potentially building a catalogue of thousands of directly imaged rogues whose properties can be characterized through spectroscopy. The characterization of rogue planet atmospheres, particularly for terrestrial rogues that might have retained habitable conditions, represents one of the most exciting prospects for future observations. High-resolution infrared spectroscopy of a rogue planet's thermal emission could reveal the presence of atmospheric gases, including potential biosignatures like methane, oxygen, or more exotic compounds that might indicate biological activity. Such observations would be extraordinarily challenging, requiring long integration times and sophisticated data analysis to extract weak spectral features from faint objects. But they are not impossible with foreseeable technology. One particularly intriguing search strategy involves looking for rogue planets that might have retained large moons, creating planet-moon systems that could exhibit detectable mutual eclipses and transits. If we could detect the periodic dimming that occurs when a moon passes in front of its rogue planet host, we would gain access to transit spectroscopy, the same technique that has been so successful at characterizing exoplanet atmospheres. The combination of a rogue planet and a large moon might even enhance habitability prospects through tidal heating, making such systems high-priority targets for detailed study if they can be found. The possibility that some rogue planets in the solar neighborhood originated from the Sun's birth cluster, and might therefore have compositions similar to solar system planets, motivates searches for rogues whose spectra or orbital characteristics might betray a solar system origin. If the early solar system ejected one or more terrestrial or ice giant planets, those planets would now be wandering the galaxy with velocities and positions determined by their ejection 4.5 billion years ago. Detailed modelling of ejection trajectories combined with surveys of the local rogue population might allow identification of solar system siblings, though distinguishing them from rogues ejected from other nearby systems would be challenging without detailed compositional analysis. Looking further ahead, future extremely large ground-based telescopes and space-based observatories might achieve the sensitivity needed to detect reflected starlight from rogue planets, opening up optical and ultraviolet observations in addition to infrared. The amount of galactic background light that a rogue planet reflects depends on its size, its surface or cloud properties, and its location within the galaxy, with rogues in regions of higher stellar density experiencing brighter illumination. While such reflected light would be extraordinarily faint, perhaps comparable to observing a barely visible grain of sand on a beach from a distance of miles, future instruments might achieve the required sensitivity for the nearest and most favourable targets. The ultimate goal of searching for wandering Earths extends beyond mere detection to full characterization and, possibly, to assessment of habitability and even to searching for signs of life. While we are decades away from having instruments capable of such detailed characterization of rogue terrestrial planets, the rapid progress in exoplanet observation techniques and in our understanding of biosignatures and habitability suggests that such capabilities might eventually be developed. The discovery of life on a rogue planet, particularly life that might have originated when the planet still orbited its parent star and survived the transition to interstellar conditions, would represent one of the most profound discoveries in the history of science. The question of whether our own solar system ejected planets during its formation and early evolution carries implications not just for understanding the solar system's history, but for connecting that history to the broader galactic population of rogue planets. If ejections occurred from our system, then somewhere in the galaxy, there may be worlds that formed from the same primordial material as Earth and the other planets, worlds that could be considered our lost siblings, now wandering alone through the interstellar dark, carrying the chemical and isotopic signatures of solar system composition. Evidence for possible ejected solar system planets comes primarily from computer simulations of the solar system's dynamical evolution and from the unusual orbital properties of some current solar system objects. The NICE model of outer solar system evolution, as mentioned earlier, proposes that the four giant planets formed in a more compact configuration and underwent a period of orbital instability roughly 500 million years after the solar system's formation. While the NICE model typically accounts for the current configuration with the four known giants, some variations of the model work better if an additional ice giant, a fifth planet with mass comparable to Uranus or Neptune, was present initially and was ejected during the instability phase. The hypothesis of a fifth giant planet has some indirect support from the orbital distribution of objects in the outer solar system beyond Neptune. The Kuiper Belt, the population of icy bodies orbiting beyond Neptune, shows a sharp outer edge around 50 astronomical units from the Sun, beyond which the population density drops precipitously. This sharp edge might be explained if a planet was scattered outward through the region, gravitationally clearing most objects before being ejected entirely. The absence of this hypothetical planet from the current solar system inventory would then be explained by its ejection during the same instability episode that rearranged the giant planet's orbits. More recent and more speculative is the Planet 9 hypothesis, the proposal that a currently undiscovered planet with mass roughly 5 to 10 times Earth's mass orbits the Sun at a distance of several hundred astronomical units, far beyond the orbits of the known planets. The evidence for Planet 9 comes from the peculiar orbital clustering of certain distant Kuiper belt objects whose orbits appear to be organized by the gravitational influence of an unseen massive object. If Planet 9 exists, its origin is uncertain. It might have formed in the outer solar system and been scattered to large distances, or it might be a captured rogue planet that the Sun acquired from the interstellar medium during its youth in its birth cluster. The distinction between a scattered planet and a captured rogue matters for understanding the planet's composition and its relationship to the rest of the solar system. A scattered native planet would have formed from the same protoplanetary disk material as the other planets and would share their isotopic signatures and bulk composition. A captured rogue would have formed around a different star and might have very different composition depending on that star's metallicity and on the composition of its protoplanetary disk. Future observations that might detect and characterize Planet 9, if it exists, could distinguish between these scenarios through spectroscopic measurements of its atmospheric composition. The possibility that the solar system once contained additional terrestrial planets in the region between the current terrestrial planets and the asteroid belt has also been explored through simulations. Some models of terrestrial planet formation suggest that more planets formed initially than survive today, with some being ejected and others colliding with surviving planets or falling into the Sun. The current spacing of the terrestrial planets, their masses, and the presence of the asteroid belt between Mars and Jupiter might all be explained partially through a history that included ejection of additional terrestrial worlds during the final stages of planet formation. If the early solar system did eject one or more planets, when might this have occurred? The most likely time for ejections would be during the first 100 million years after the solar system's formation, the period when planet formation was completing and when gravitational interactions between forming planets remained strong. The late heavy bombardment period, roughly 3.8 to 4.1 billion years ago, might have included ejections associated with the giant planet instability. After that period, the solar system appears to have settled into its current stable configuration, making subsequent ejections unlikely barring an extremely close encounter with a passing star, an event that probably has not occurred during the solar system's history. Where would ejected solar system planets be now, 4.5 billion years after their ejection? They would be scattered throughout the galaxy, following galactic orbits determined by their ejection velocities and the Sun's motion through the galaxy over billions of years. Most would likely remain within a few thousand light-years of the Sun's current position, but individual objects could be anywhere within the galactic disk, depending on the details of their ejection and subsequent gravitational interactions with other stars. Finding them would require identifying rogue planets whose compositions match solar system material, a challenging task that would require detailed spectroscopy of many rogues to search for the distinctive patterns that characterize our planetary system. The isotopic composition of solar system material, particularly distinctive isotopic ratios of oxygen, silicon, and other elements that resulted from the specific mixture of materials in the Sun's protoplanetary disk, provides a potential fingerprint that could identify solar system origin. If we could measure these isotopic ratios in rogue planet atmospheres or surfaces, we might be able to determine whether specific rogues formed in our system. But such measurements lie far beyond current capabilities and would require future generations of instruments with sensitivity far exceeding anything now available. The contemplation of solar system siblings wandering the galaxy connects our own planetary system to the larger story of rogue planets throughout the Milky Way. If we lost planets to interstellar space, then we contributed to the rogue population just as other planetary systems did. Somewhere out there might be worlds that formed from the same cloud of gas and dust that gave rise to Earth, worlds that might have developed in ways similar to Earth before their ejection, worlds that in some sense could be called our kindred, despite their current isolation and despite the billions of years that separate their history from ours. As you drift now towards sleep, let your mind's eye follow these lonely worlds on their eternal journey through the spaces between stars, spinning silently in the darkness, illuminated only by the faint, distant glow of the galaxy itself, following orbits around the galactic center that will carry them through the eons, long after our own sun has exhausted its fuel and faded to a cold white dwarf remnant. The rogue planets, these wanderers in the cosmic dark, remind us that the universe's creativity in making worlds far exceeds the tidy arrangements we see in stable planetary systems, that for every planet blessed with the warmth of a nearby star, there might be one or more siblings cast into perpetual night, experiencing existence in ways we can barely imagine. What profound loneliness must characterize the experience of a rogue world if we could somehow grant it consciousness or awareness? To have once known the light of a sun, to have formed in a disk of dust and gas surrounding a young star, perhaps to have developed an atmosphere, and oceans and even life during an early period of normal planetary existence, and then to have been flung away through gravitational violence into darkness that would never end, into cold that would eventually freeze every molecule, into isolation so complete that even the nearest star remains forever out of reach, across distances measured in light years. Yet perhaps this loneliness is purely our projection, our habit of understanding experience through our own perspective, as creatures evolved on a world bathed in starlight, unable to conceive of existence without the rhythms of day and night, of summer and winter that our sun provides. The rogue planets teach us that our solar system's arrangement, stable and predictable and lit by the sun's steady radiance, represents just one possible outcome of the planet formation process, perhaps even an unusual outcome. The universe seems to make rogues readily, perhaps as readily as it makes stars themselves, filling the galaxy with dark worlds we are only beginning to detect, populating the vast emptiness between stellar systems with objects we might never have predicted were there. This hidden complexity, this revelation that the spaces between stars are not empty, but rather filled with wandering worlds, transforms our picture of the galactic landscape from one dominated by stellar islands, separated by vacuum, to one filled with structure at every scale. Here on Whispering Universes, we have explored how these worlds came to be, how they might maintain liquid water, and perhaps life beneath frozen surfaces, how we detect them through their subtle gravitational signatures, and how our own solar system might have contributed its share of rogues to the wandering population. We have contemplated their journeys that span billions of years, their rare encounters with stars that almost never lead to capture, and the possibility that some among them might harbour life sustained not by sunlight, but by geothermal warmth and chemical energy, ecosystems that have never known a day and never will. As you feel the boundaries of waking consciousness dissolving into sleep, as your thoughts become less linear and more dreamlike, imagine the galaxy as it truly is. Not just bright points of stellar light, but countless unseen worlds between them. Orphaned planets carrying the history of violent scattering events billions of years ago. Young rogues still warm from recent ejection. Ancient rogues cooled nearly to the temperature of the cosmic background itself. Wanderers beyond counting, moving through the darkness on paths that will never bring them home. They are there, invisible but real, detected only by their gravity's effect on light or by their faint infrared glow, filling the cosmos with planetary diversity beyond what our star-centered thinking could have predicted. Thank you for journeying with us tonight through the realm of rogue planets, the wanderers without a sun. Let these thoughts of dark worlds and long journeys carry you gently toward rest. Let the vastness of the galaxy's hidden population inspire peaceful dreams of cosmic complexity, and sleep well knowing that the universe holds more wonders than we have yet begun to comprehend, more worlds than we can yet imagine, more stories than we will ever fully tell. Sleep peacefully, dream deeply, and may your thoughts drift among the stars, both the bright ones we can see and the dark ones that wander between them. Until we explore together again, this is Whispering Universes.